We continue to learn Chapter 4, Linear Transformations. Section 2, Matrix Representation of Linear Transformations. Part 2, Matrix Representation of Linear Transformation L from V to W, where V and W are general vector spaces. Let E equals V1, V2 till Vn be an ordered basis for V of dimension n. And let F equals W1, W2 till Wm be an ordered basis for W of dimension m. And let L be a linear transformation mapping V into W. We want to show that for every vector V in this vector space V represented in terms of E as this V. So V equals x1 the scalar times V1 plus x2 the scalar times the vector V2 plus TL plus xn times Vn. So this means we write V as a linear combination of a given basis vectors here in vector space V. And there exists an n by n matrix A representing the linear transformation L in the sense that Ax equals y if and only if LV equals y1 w1 plus y2 w2 plus TL plus ym wm. So what does this mean? So here you have two bases. One basis is for V. Another basis F is for W. They are two different vector spaces. And here X is a coordinate vector with respect to E. Okay, and here Y is a coordinate vector with respect to F for the linear transformation L function on X. So here Y equals Ax if and only if LV can be written in this form. So you use the basis vectors W1, W2 till Wm and Y1, Y2 till Ym. It's just the coordinate vectors. Okay. Let us denote AJ just by A1J, A2J till AMJ, a column vector of LVJ with respect to F. So this means you represent LVJ by linear combinations of W1, W2 till Wm, where the scalars before those basis vectors are A1J, A2J till AMJ. Okay, so this means AJ is the coordinate vector of this LVJ with respect to F. Okay, and then we let A equals Aij. That is A composed by these column vectors A1, A2 till AN. So they are the coordinate vectors of LVJ, where J varies from 1 till N with respect to this given basis F. Then we know LV just equals L function on this one. Summation J varies from 1 to N, xj, vj. So this one just come here. Right? We substitute V by the linear combination of given basis vectors in space V. And then because this is linear transformation, so we can put these scalars out, which equals the summation J varies from 1 to N, xj times LVJ. And again, LVJ has this representation here. LVJ can be written as a linear combination of W1, W2 till Wm. So we write it here, which equals summation I varies from 1 to m, Aij times Wi. And because they are finite sums, so we can transform the position. Here we put I varies from 1 to m first. And here, this relates to J. J varies from 1 to N. We change the order of these two summations, and this one times Wi. So this means we can represent LV by the basis vectors Wg given in F, where the scalar before each wi is this one, summation j varies from 1 to n aij xj, and this one should be just yi. Okay, so we let yi equals summation j varies from 1 to n aij times xj. For I varies from 1 to m, that is, we have this one, y equals a times x, which represents the coordinate vector of LV with respect to the basis f. Okay, and then we have this theorem 4.2.2. If E given and F given are ordered bases for vector space V and W respectively, then corresponding to each linear transformation L from V to W, there is an n by n matrix A such that we have this coordinate vector of LV with respect to F just equals A times the coordinate vector of V with respect to the basis E for each vector V in the vector space V. Here, A is a matrix representing L relative to the ordered bases E and F. And in fact, we know that AJ, the jth column for A, just equals the coordinate vector of LVJ with respect to the given basis F for each J, varies from 1 to till n. Okay, this matrix representation theorem can be understood by this figure. See, here you have a vector V belong to the vector space, capital V here, and here L is a linear transformation. We write L equals LA. Using this linear transformation, V becomes now W. So W equals LV belong to the vector space W. And in fact, for any vector space, the coordinate vector is related to the basis you given. Okay, so suppose for the vector V, you give this basis E. Okay, so with respect to this basis, you will have the coordinate vector X, which equals the coordinate vector of V with respect to E. Okay, so V is a vector. X is a corresponding coordinate vector with respect to the given basis E. Okay, and similarly, here, for the linear transformation, we say there's a matrix corresponding to it. It's a matrix representation of this linear transformation A. Okay, so A times this coordinate vector X, you will get a new coordinate vector Y. So Y equals A times X. Y equals A times X, which is also the coordinate vector of W, where W equals LV with respect to F. See? So A just maps X to Y if and only if L maps V to W. So A is a matrix representation of L. Clear? Okay. Now we consider simple example. Example 3. Let B1 be given 1, 1 transpose, and B2 given minus 1, 1 transpose. Let L from R3 to R2 be defined in this way. So L of X equals X1 times B1 plus this scalar X2 plus X3 times B2 for each X belong to R3. Ask you to find the matrix A representing L with respect to the ordered basis E1 into E3 and B1, B2. So this means for the original R3 space, the basis is E1 into E3. And for the R2 space, we use the basis B1 and B2. Okay, and then we can write L of X equals A times X, right? So Y should equals A times X. y is just here is x1, here is x2 plus x3. So it equals this matrix 1, 0, 0, 0, 1, 1 times this vector x1, x2, x3. So the matrix A can be obtained easily from this expression of L of x, because this L of x, in fact, just use the standard basis E1, E2, E3 to this B1, B2, and write also in the coordinates vector of B1, B2 already. So you can obtain immediately A equals 1, 0, 0, 0, 1, 1. Because if you times x1, x2, x3, you will get x1 for the first coordinate, and x2 plus x3 for the second coordinate. Okay. And now we see this example. This example, let L, a function on alpha b1 plus beta b2 equals this scalar alpha plus beta times b1 plus 2 times beta times b2. Let this be a linear transformation mapping from R2 to itself, also R2 to R2. Ask you to find the matrix A representing L with respect to the basis B1, B2. So for this example, for the original and the mapping vector space, they are same. They all R2 space. And also the basis vectors, the basis, they choose the same basis, each composed by B1, B2. And the linear transformation is defined in this way. So from here, for the x is coordinate vector corresponding to B1, B2 is alpha, beta, see? And for the new vector, after you do this linear transformation, you get a new vector. The new vector is coordinate vector corresponding to B1, B2 is alpha plus beta, 2 beta, see? So you should have this y equals A times x. This means you should find this matrix such that alpha plus beta, 2 beta should equals this matrix times alpha beta. So of course A can be obtained easily. So A equals the first row should be 1, 1. The second row should be 0, 2. Okay. Now we see example 5. The linear transformation D defined by D function on this polynomial function P equals P derivative. This one maps P3 into P2. So P3 is a set of polynomials of degree less than 3, and P2 is a set of polynomials with degree less than 2. Okay, given the ordered basis here and here for P3 and P2 respectively, so they are the standard basis, right, for those P3 and P2 here. First question, Q1, determine a matrix representation for D. And in order to determine this matrix representation, so we using this linear transformation function on those basis vectors. The basis vectors is x2, x and 1 respectively. So D function on x2 will gives you 2 times x plus 0 times 1, and D function on x will gives you 0 times x plus 1 times 1. And D function on 1 will gives you 0 times x plus 0 times 1. And then because x1 is a basis for P2, so it's just can give you this matrix representation. The matrix representation should be 2, 0 for the first column, 0, 1 for the second column, and 0, 0 for the third column. Okay, so you have this matrix representation of L. And Q2, question 2, if Px equals A times x power 2 plus B times x plus C, ask you to determine D of P by using A. So if Px equals here, then we know it's coordinate vector with respect to those bases, x power 2, x1 is A, B, C. And we have this matrix A, matrix representation for the linear transformation. So coordinate vector with respect to x1 in P2 is just obtained by this A times the coordinate vector here, ABC. And you will get is 2A and also B here. So you know the differentiation at this operator function on this ax power 2 plus bx plus c will gives you 2a times x plus b.